Well, greetings, mathletes, and welcome back. We are going to be talking about continuity today. Now, continuity turns out it's much what you expect it to be. A function is continuous, basically, if you can draw it with a pencil without lifting your pencil from the page. I mean, that's probably the simplest definition of continuity. And really, a lot of the time, we decide if something is continuous by looking for places where it is discontinuous, right? So it actually helps to have an idea of what a discontinuity looks like. And so we're going to look at a few of those, and then we're going to look at the actual definition of continuity at a point, and just kind of explore some of its consequences. All right, so let's go ahead and get started here. There we go. So again, continuity, a continuous function. Oh, I always forget to change that. Oop, too small. There. Okay, let's try that again. So a continuous function, basically, and we talk about a function being continuous on an interval or continuous at a point. Basically, the idea is the function's continuous if I can draw it in one swoop, right? Something where I don't have to lift my pencil. Things that are not continuous, we've seen some of this stuff already, where you have a hole in the graph, right? That's a type of discontinuity. In fact, that's called a removable discontinuity because we can get rid of it just by plugging the hole. And another type of removable discontinuity, sometimes instead of being completely undefined there, you have a separate point it's broken out of the function, right? So this is discontinuous, right? And these are removable. Okay. Now, there are also discontinuities. We've seen some of those, like with the function absolute value of x over x, or x over the absolute value of x, right? You end up with a jump discontinuity. Right? You end up with something like this, right? So if this is the point C, we would say this function is discontinuous at C, whatever that happens to be. Same thing here. If this is the point C, this is discontinuous at C. This is called a jump discontinuity. Let's spell that a little better. Right? And a jump discontinuity, well, they happen in piecewise functions a lot too. Okay. Then we have, let's see here, I can just do it over here. We'll get rid of that. Other types, we have infinite discontinuities. Right, and those are asymptotes, where you have something like this, and maybe you have two things that go up like this, right? That happens from time to time. Sometimes you have them so one goes up and one goes down, right? These are infinite discontinuities. And they're the ones that part of the function goes off into infinity, basically, is what happens. And so you can't draw it continuously with one pencil. Let's see. Oh, and then the last one is the oscillating. Discontinuity. Now, these are weird. We're going to see some of these from time to time, but usually they're given as counterexamples to things. But for example, the graph of sine of 1 over x is one of those ones that has an oscillating discontinuity, because what happens as you approach 0, this quantity inside goes to infinity, right? It gets bigger and bigger and bigger. And so the effect is all of the sine oscillations that go off to infinity all end up being compressed down into this little section here, right? So you end up with a sine curve, but the period changes and it gets higher and higher and higher, or excuse me, the period gets shorter and shorter as you approach the as you approach x equals 0. And so you end up with this weird little oscillation, and it just kind of goes crazy as you go down to as you get close to 0, because it just oscillates faster and faster and faster. So that's another type of discontinuity, although we don't run into those quite as often. We're really going to be focusing more on the removable discontinuities and the infinite discontinuities throughout this semester, because those are the ones that pop up with polynomials and rational expressions and things like that. Those are the ones that are a little bit, well, they're a little nicer to deal with too. Okay, so that's what a discontinuity looks like, right? It's the place where you have to lift your pencil to keep drawing the function. Okay, so now let's go ahead and take a look at the actual definition. Do I want to go that far? Yeah. Okay. A function f is continuous or not on, but at C. At C, if and only if, so that double F if means that this is a definition, right? It means if and only if. The limit of f of x as x approaches C is the same thing as just plugging C into the function. So we've seen a lot of these, right? If there's no discontinuity there, all you have to do is plug in the value. And so we've taken advantage of this because we know certain functions are continuous, like polynomial functions and things like that. We've kind of just taken it for granted up until now. So this is what it means. What it means is basically while you're drawing the function, there's no holes, but everything is exactly where you expect it to be. If you were on that function driving, right, there's no jumps in the road, is basically what this says. Everything's exactly what you expect it to be when you get close to it. So there's certain rules where we can manipulate some of these things. If we know certain things, if we know functions are continuous, they have properties. So if f and g are continuous functions, then the following is true. Okay, 1. F plus g or minus g is continuous. Actually, all of these are going to end with is continuous. 2, the product of two functions is continuous. The quotient of two functions is continuous. Well, I'll put it this way. It's continuous where g of x is not equal to 0, right? Because you don't want to be dividing by 0. Okay. Also, you can multiply a function by a number. K is just some number. Right, so that's continuous. And then also powers. If I raise f to the n power, that's also continuous. And roots, right? The nth root of x, or f, excuse me, is also continuous, right? So that basically that's the algebra of functions, right? So basically what it's saying is that functions are continuous under their algebra, right? Whatever the algebra of functions does, it produces continuous functions as long as you put continuous functions into it, right? With the exception of division. And we know division causes problems even with regular arithmetic. You can't divide by 0. Okay, now there's one more thing, and this one's a little bit more tricky. The last one has to do with taking taking limits where under composition, right, f composed with g, if actually I want to write it this way. If the limit of f of x as x approaches c is equal to b, then, and this is also, and g is continuous, what ends up happening is that the limit of g of f of x under the composition as x approaches c is equal to g of b, right? So whatever the limit, so basically what this is saying is if you have a composition, if you have one that's not continuous, I shouldn't have done that. We don't know if f is continuous or not. All we know is that the limit exists at c. As long as the limit exists, you can just plug the limit into the outside function, is basically the idea here. So these are like the main rules, right? And I would actually advise getting a list of these just so you have them handy, just so you can check. I think most of this stuff, though, will end up coming a little more intuitively. You'll use these rules without really thinking about the fact that you're actually using the rules. Okay, so let's go ahead and clear that out. Okay, so one of the tasks that you're going to need to be able to do is find where a function is continuous. So let's say I have y equals 1 over x minus 2 minus 3x, right? And we want to know where this function is continuous. Well, we know we can actually decide certain things about continuity just by looking at the two terms here, right? This one is continuous everywhere because it's a polynomial. Polynomials are continuous everywhere. They have no holes in them. They have no gaps. They have no jump discontinuities. There's no discontinuity of any kind in a polynomial. So I don't have to worry about this one. This one, though, is a rational expression. And so anywhere the denominator is 0, and by the way, that's mostly what we're going to be focusing on is when the denominator is 0, it's going to cause a discontinuity. So if you want to know where the denominator is 0, you take the denominator and set it equal to 0 and solve the equation. Now, you probably did this in your head already, just looking at it. You probably looked at x minus 2, and you know if you plug in 2 for x, you're going to get a 0. I'm demonstrating this is what you end up doing pretty much with everything. So sometimes you can do it in your head, sometimes you can't, but just know that what you're doing is setting it equal to 0. So what this means, and actually, if you want to be technical about it, it's technically saying it's not equal to 0 and solving the equation. So x can't equal 2. Now, in a lot of contexts, that is perfectly good. Hey, the discontinuity is at 2. X can't equal 2. But we're going to need to write it in interval notation. So basically what this says, if x is not equal to 2, right, here's our number line, and basically I have a hole here at 2. And so I need to note the interval up to 2 and the interval above 2. So I'm going to write them down separately. If you're familiar with the interval notation, this won't be any problem for you. But if you're not, this interval here, this line segment starts at negative infinity. So I'm going to start my interval here. It goes up to 2. It has a round bracket because it does not include 2. And then it continues afterwards. It has a round bracket again because 2 is not included. And it goes up to infinity. And then to show that it's part of the same solution, you put a union between them, right? So that's our interval notation. This is basically the places where this function has values, right? This interval tells us exactly what things we're allowed to plug into this function. Because if you plug in something out of discontinuity, you might have problems. Sometimes it's undefined, sometimes it's not. But um, this is the places that it's continuous. Okay, so that's the first one. And again, we're going to be really focusing on looking at these denominators. All right. So let's say I have, let's make it look a little more scary, although it's not. Let's see, we got x squared minus 4x plus 3. Okay, so and we want to take this and figure out what values cannot be in the denominator. You notice I'm not graphing it. Sometimes that does help if you know something about the graph, especially with the trig functions. But in this case, where I'm just looking at a rational expression where it's a ratio of two polynomials, I just need to take the denominator and set it equal to 0 to solve, to figure out what values I can't have. And I'm saying set it equal to 0, but it's really a not equal to 0. Let's see, that factors. And let's see here. So that's going to factor as x minus 3, x minus 1. And so I end up with that. And so x cannot equal 3 and x cannot equal 1. Right? So I have those two gaps. So if we look at a number line again, I have holes at 1 and at 3. And we can see there's 3 intervals. I have this guy, and this guy. So I'm going to have 3 pieces to describe this time. So the first interval goes from negative infinity up to 1. The second interval goes from 1 to 3. And the third interval goes from 3 to infinity. Right? And I just, to show they're all part of the same solution, I add that union in there. Right? And so this is our answer. This is the region where f, or not f, this function is continuous. We haven't called it a name yet. It's y, I guess, y of x. In any case, if you're not familiar with the interval notation, it's a really good idea to familiarize yourself with it because it gets used a lot throughout calculus. Okay, so let's look at another example here. Let's actually put some trig into this. Okay, let's look at y equals cosine x over x. Okay, so we have 2 functions here. One of them is a polynomial, one of them is not, right? The denominator is a polynomial, the numerator is a trig function. So the first thing you want to ask yourself is cosine discontinuous anywhere? Since it's not a polynomial, you know, we can't just assume it's continuous. But from what we know about cosine, you know the graph of cosine, it does the whole wave thing here. That's a terrible cosine, but there's no holes in it, is the main point. Oops. So because there's no holes in it, we know it's continuous. All right, so that means we're left with the denominator. And, well, basically we're okay as long as x is not equal to 0. I don't even have to solve anything. I'm just looking at it. If I make x 0, I have a problem. I have 1 divided by 0. So that's the entire interval. And again, or excuse me, not interval. That's the excluded value. So here it's 0. So I have an interval coming up here and an interval on this side. And I have the interval from negative infinity to 0. And I'm going to union that with the interval from 0 to infinity. So basically it just starts at negative infinity, cruises up to 0, jumps over 0, and then keeps going on to infinity. Right? So this ends up being our the area where this is continuous. Right? So that was a pretty straightforward one. Now, some of them you have to do some work. Okay, so let's take a look at one that we have to do a little work with. Because, well, we'll take a look at it first. Let's see, y is equal to tangent of pi times x over 2. Okay, Now, we don't have any denominators here, right? So that seems to cause some issues. But we do know that tangent has asymptotes. If I just look at one period of tangent, it goes, I have an asymptote here at negative pi over 2. I have one at pi over 2, right? And this guy, it goes up on this side and down on this side. And it repeats itself. So I have another one doing this on this side, and I have another thing going over here on this side. So these asymptotes are going to repeat, right? Because that means that I have to have another one out here at 3 pi over 2. Right? So we have an infinite number of these discontinuities in this thing now. Right? So we have to be able to accommodate them somehow. So, first of all, this is not where the discontinuities will be with this function, because if I look right here, I'm multiplying pi over 2 times x, and that is going to alter the period of the function. So we have to figure out where that goes. So here's a nice trick. When you want to see where the asymptotes of tangent go, you know where they start out, right? They start out at, I get asymptotes if x is equal to negative pi over 2 or pi over 2. So I'm just going to look at one period of this to start out with. So what that means is I can take this pi over 2 times x, and I know my endpoints here, negative pi over 2 and pi over 2, I can just stick those asymptotes on the outside. What I do now, and you could do this actually with any of the trig functions that have asymptotes. If you know where their asymptotes are, take the argument of the trig function and put it between the asymptotes, and then solve for x again. And that will tell you where the new asymptotes move to. So what we're going to do here is divide everyone by pi over 2. Right? So, well, it's basically a number divided by itself all the way across, right? That cancels. This is negative 1 to x to 1. So what that means is now this tangent curve, instead of having its asymptotes at these values, they've been moved to negative 1. Let me switch colors so it stands out. To negative 1 and 1, which means that the period is now 2, right? So it's 2 units across, which means the next one up here is going to be at 3. So that means I add another 2 here. The next asymptote is going to be 2 more than that, and I can do the same thing in reverse. I can go minus 2 in this direction to find the next asymptote. So I know the asymptotes are 2 units apart. Okay? What that means, and there is some really fancy notation for talking about unioning a bunch of intervals together, but we're not going to be using that at this point, is that I have discontinuities at x is equal to 1 plus 2n, where n is an integer. Well, that didn't work. Try that again here. We'll just, that says integer. Here's the nicer way to write that. N is an integer can be written this way. Right? That means take n from the list of integers is what this means. And yeah, the double stamped z is the math symbol for an integer, just like the double stamped r is a math symbol for the real numbers. It's the same kind of thing. If you've taken me before, you've probably seen that notation because I'm lazy, and that notation is much easier to use. So in any case, some of these trig ones get a little bit dicey, but that's the bottom line. Start at 1 and then just add and subtract 2. And I know this is a plus sign, but not all integers are positive. You can pick negative integers also, and that takes care of moving in the negative direction. So, okay, so those are our main examples as far as that goes. Now I want to get to some technical details. So let's see. Okay, so one of the technical things I wanted to talk about is the handedness of continuity. So right and left-handed. So right and left-handed continuity. Um, these types of things basically happen when you have usually it's some kind of jump discontinuity where you have something that does this, right? Where you have a hole here, right? So let's say that's our function. Um, Basically, if I look at this function, I'll call it f, right? If I take f of x and I look at the limit of f of x, oh, and then let's go ahead and call this c. There we go. We want to look at the limit of f of x as x approaches c from the left. Okay, in fact, let's go ahead and just say that that's 3 and that's 1, just so we have some values. Okay, so the limit as f of x approaches c from the left-hand side, right? So coming in from this side right here, is equal to 3. Right? But the function value, f of c, isn't equal to 3. There's a hole there. The function value is at 1. Okay, so it does not have left-handed continuity. So because these two guys don't match, so there's no left continuity. Right? Okay, but if we look at it from the other side, because you remember that definition is that f of x, what was it? It was the limit of f of x as x approaches c is the same thing as plugging c into the function value. And you can see that doesn't work here. I don't get the same value. But if I come in from the other side, the limit as f of x approaches c, or x approaches c from the positive side, right, I get 1. And f of c is also 1. And so this is continuous from the right-hand side because these guys match. Right? So I have right continuity. So that's just kind of a technical point. It doesn't come up all the time, but it does come up occasionally, and you should pay attention to it. Right? Just kind of note in your head when you look at these things. It's continuous from this side, not from this side. And basically the side that has the hole is the side that it's not continuous at. It's going to be continuous where the hole is plugged, basically. Now, the other thing that I want to talk about is the intermediate value theorem. Oh. Okay. Sometimes it's just called the IVT. Right, just so you know, that gets used often enough that it has its own abbreviation. But it's a really simple idea. The idea is if I have a continuous function, f is continuous, right? So we know that. And, right? And I'm just going to pick 2 points. I'm going to pick, actually, let's pick a lower point. We'll call this A, and we'll call this point B. Right? So the x values are A and B. Okay, so f is continuous on the interval from A to B. Right? Actually, let's make it a closed interval. I think it'll... It's fine either way. There's a lot of technical jargon in this, but basically, as long as it's continuous, from A to B, then it assumes every function value in between, every y value in between f of a and f of b. So this is f of a, and this is f of b. These are both y values, and so basically it says that as long as it's continuous from here to here, then anytime you draw a horizontal line that's between these two values, you're going to hit a piece of the function. That's basically what it's saying. And it seems like a really overly simple idea that, yeah, if it's continuous, it's connected. That's really what it says. The consequence ends up giving us a leg up when we're doing things like looking for roots. Because a root is basically an x-intercept. It's where it crosses the x-axis. So if you can find an a and b, right? Let's say this is our function, right? It does something like this. So that's f of a, and then f of b is down here. The idea is that if f of a is greater than 0, if one value is bigger than 0 and the other value is smaller than 0, then between those two values, between this positive and negative number, there has to be some value that gives you 0, right? So what we say is there exists a 0 on the interval from A to B. So I'm going to write this in a different color because I want it to stand out here. So because of this and this, because I have two values that are on opposite sides of the x-axis, that means it has to cross the x-axis to get from one to the other. And so we say that there exists, now this is getting a little ahead of your book, but I like to use abbreviations. A backwards E means there exists an x on the interval AB so that f of x is equal to 0. So basically what you've just done is show that there is a root. There is a solution that gives you a 0. It crosses the x-axis somewhere. And it's a very strange kind of a thing because it seems obvious, but it really does take some work to prove it. And as far as this notation goes, again, it's just there must exist a 0 in here is what it says. Now the notation I'm using, well, I'm going to keep using it just because it takes less space in the long run. But in any case, that's the last thing. And we're going to be using that more later on in the semester. Again, this is one of those things that's getting introduced early so that we can reference back to it. But anytime you want to show that there's a root to something, all you have to do is find a positive value and a negative value for the function. And then somewhere between the two x values that you used, there has to be an x value that will give you the 0. So in any case, let's go ahead here. Let's do that. Yeah. So this will go ahead and conclude our lecture. Again, please feel free to ask me questions. I've made myself pretty available to you guys. And anyways, until next time, keep your pencils and your wits sharp.